Okay. This isn't a complete presentation. This is just part of the development. And so, if you're saying this, I've already gotten the presentation or it was rejected. But I don't think I'll post this until it's done. This is just kind of for me to review. This might go public, maybe not. But I'm going to just try to go over this and see how it kind of times out. Um, and begin. Hi, everyone. Thank you for coming to my talk. I'm going to talk about the physics behind energy and nutrition, and I'm going to give us a fresh understanding. I don't really want to go into my details on who I am, so I just did a quick little intro. Instead of starting with the introduction, I'm going to start with my conclusions. First, that calories are not a valid model of thermodynamics for nutrition and exercise. We do have an understanding of thermodynamics, molecular, particle, and quantum, and we have the opportunity to advance our field, but we have to be brave if we want to do it because we have to get into physics. And that's because physics sets all the rules, and we have to have an understanding of modern physics. Um, it has to be in agreement with where we're at. I'm doing terrible. Physics is the scientific study of matter and its fundamental constituents, its motion and behavior. I was just reading it. Um, Physics is a scientific study of matter and its motion through space, its related energy and forces. It's one of the most fundamental scientific disciplines. It's just to not make it scary, to make it simple. It's the study of nature and how nature works. It comes from the Latin and the Greek, just the study of nature and natural science. And so the physics of nutrition is understanding how the food we eat becomes the material and structure for the function of becomes the material for the structure and function of organs, tissues, and cells. Physics and science of any subject makes accurate, reliable, and valid measurements. And so let's get into the history and respiration. The history of calories. We start with the prehistory. The first measured relationship between respiration and carbon combustion is 1783, and the first calorimeter is also in 1783, but they didn't have the word for calorie yet, so they just called it the calorimeter. Um, this is by Lavoisier and de Laplace, and the guinea pig is there because they used a guinea pig. Um, well, I don't have to mention that part. So the idea was that if you can, we can measure the temperature of something by the contact, but that really just measures like the ambient temperature. You're not measuring the exchange or the release. But if you could surround something with ice, then you could measure the release of heat into the ice, and then that ice would melt, and you could weigh the water, and more heat would just melt more water. Is the simplest way to is the experiment. And so he built this machine so you can have the experiment or the object for respiration. He measured a guinea pig. In the calorimeter, you fill the second chamber with ice, which drips down below into a receiver, as you can see. In the third chamber, I believe you fill with ice. I'm going to check it again, but that's just to uh, be aware of atmospheric pressure. Um, Damn, I'm so far behind. Okay, 3 minutes in. So the math. So this is how he came up with that. Respiration is like carbon combustion. The analogy between. These are his math showing it. And so calories came in 6 years later with the Traité élémentaire de chimie, elements of chemistry in English. So calories are, according to Lavoisier, particles of matter produced by fire. They're particles of matter. It's to obey the conservation of matter. They combine with particles of bodies, warming them and expanding them. Particles of matter produced by fire bind to particles of body, warming and expanding them, and separate from them, cooling and shrinking them. And they'll change their affinity to liquids depending on atmospheric pressure, because water boils at higher pressure. And just as a concept, it was the separation of particles as heat is the main concept, but everything else is hypothetical. I should change this. Be more. Um, and so food and respiration composition, just to go over again, is proved to be similar, giving external validity to our document. Inputs and outputs. Kind of like having validity up front. Yeah, this is 5 minutes in. I think I could do this. And then we get into Helmholtz and the idea of craft, the idea that all energy in the universe is conserved. So we can take this heat energy and we can there's got to be something about the material that we eat and the exchange between everything that transfers energy. That's the idea between craft. And the idea that physiology and nutrition is essentially just this combination is the essential idea behind craft. Um, I don't have time to look it up. Like, there's plenty of time. Um, Marx. Oh, that's William Grove. To talk about Rubner. Yeah, even physical labor could be explained by fire. And like heat and movement. And then Murray, Etanid Jules Murray, continued this idea. That the animal organism is no different from our machines, except for their greater efficiency. Hardly universally accepted among French physiologists, those who were still attracted strongly to those of Claude Bernard. 1867. All that we know, the science of life can be explained by the laws of physics and chemistry. Bernard maintained the truth of biology could be revealed only in the living organism, not in a general view of nature, nor in physics or chemistry. So while we agree with Murray, we don't necessarily agree with. Well, they were very different from his machines, more close to our machines, not his machine. Um, combustion, Murray, energy transformation, von Voigt. He thinks that all energy is moved from nitrogen and nitrogen movement, but this can't be completely established. So then his student Rubner comes in and is able to establish that each of these molecules, carbs, fats, and proteins that are essential nutrients, also supply enough energy to maintain normal health and like temperature of the body above a fasted state. And he determines these 494 rule. But he also explicitly says like it's not good enough for this, it's not good enough for that, because we don't know this and that, and we don't know this and that. And I should also put in what the limitations that Lavoisier said. Um, and then I'm going to spend a bit on Lavoisier, go to Helmholtz, Jules, and Bernard, physiological materialism, surrounding the bend, 30 seconds, on Voigt, Rubner, Atwater, molecular theory, electrons, physics, classical mechanics. Okay, that's 10 minutes. Not great. Technically did not finish. I'm gonna put this back. Oh, I'm still recording. Okay. Um, let's try this again. I give this one more try, then I might go to the gym. See what happens. All right. Ready and go. Hi, everyone. This is going to be the physics behind nutrition. It's going to be a fresh understanding. Um, I don't, I don't really want to get into who I am. We'll get into the science. We'll get into me at the very end if you need to. So I'm going to start with my conclusions first, and then we're going to work backwards from there. Um, so the calories are not a valid model of thermodynamics for nutrition and exercise. We do have an understanding of the thermodynamics for nutrition and exercise, their molecular, particle, and quantum. And we have the opportunity to advance our field, but we have to be brave because we have to take on physics. Physics sets up the ground rules. And I know physics can seem scary. I mean, it's the study of matter, it's the study of motion and behavior through time and all the energies and forces. But really, we could simplify it, and physics is the study of nature and how nature works. It is just the study of nature. So the physics of nutrition is understanding how the food we eat becomes the material for the structure and function of organs and tissues and cells. I was a little late on that timing, but physics and science, blah, blah, blah. Physics of, in science of any subject needs accurate, reliable, and valid measures. Validity of a measurement is the most important characteristic of a measurement, measuring what we intend to measure and correctly interpreting and applying these measures. There are types of validity I'm not going to go over, but I will color code them to make them a little bit more easy. We will go over these as we go over the slides, and these are the specifics onto each part of the slides, and we'll get to them as we get to each part. Construct and content validity we'll get to last, and we will show you how the red is what I disagree with. The green is what we're good with. Okay. So the construct question is: food supplies the body with energy for muscular work. Do calories correctly measure that behavior? And the claim, the content validity is that calories measure the physiological transformation of food matter into thermodynamic energy for movement and cellular activity, similar to food combustion. Okay. And so where do we get calories from? So this is a history of heat and respiration. Um, First measured relationship between respiration and carbon combustion was in 1783 by Lavoisier and Pierre Simon de Laplace. That's actually how I spell his name. The first calorimeter, originally called the machine, was also in 1783. The idea is that with the thermometer of mercury, you can measure the temperature that interacts with the mercury, but you can't measure the temperature of the reaction and how much heat is released. But if you were to trap that reaction in a ball of ice, you could measure the heat released into the ice, and you could measure the weight of the water, thereby measuring the amount of calories produced by the experiment. This is the first calorimeter. You could see in the middle is where they would put the object or the item, including the guinea pig, which is how they did respiration. And they'd put ice in the second chamber, and the third chamber was as a buffer. This is how carbon and respiration were drawn together in 1783, and then calories were later invented 6 years later in the elements of chemistry. And the calories, according to Lavoisier, are particles of matter that are produced by fire. They could bind to particles of bodies, warming and expanding them. They could separate from them, cooling them, and they will change their affinity depending on atmospheric pressure. Um, the separation of particles of heat is the law of nature, and this repulsive force is what we are trying to identify. Allowing the existence of these fluids to be hypothetical, strictly speaking, we're not obliged to suppose these to be a real substance. This way, we could just investigate them as an abstract matter. This was Lavoisier's thought. These are not, he is not claiming to say that this is real physics. He's saying that this is a good mental model to help us understand because, and I'll show in the next slide, that we do not have the tools to understand everything that we need today. That's what Lavoisier says. So he's not arrogant enough to assume that he knew. Food and respiration composition, I already went over, so I could delete that slide. So now we get into the 1800s because Lavoisier unfortunately died. Uh, the In the mid 1800s, this guy named Helmholtz, he was a great physician and philosopher, and he spoke to this universal constant energy. Lavoisier came up with the idea of conservation of matter. That's how he came up with the fire matter, so that matter could be added as heat. These particles of matter, expand. And we would later, it would take 100 years to find out that this is not the case. Um, I should probably put that in there too. And then, boom. Okay. So, um, Helmholtz had this idea of universal energy that all things can be as energy is conserved. So that way we can measure, if we can measure energy in one way, we have a Rosetta Stone to measure energy in all the different ways. Um, and so from this philosophy, people began to try to measure where does the energy for food come from. Von Voigt, who figured out the original nutrients, thought that this energy came from nitrogen, from protein decomposition, but through a bunch of experiments, we showed that this was not the case, that protein composition was affected by other factors, not just energy expenditure. And his student, Max Rubner, thought that energy expenditure was determined by the isothermodynamic properties. And this was from the studies of first he did these studies and then he did the 1905 studies, and then that's where we get the like whatever it is because I gotta go finish reading it. um, and then we get to Atwater, and then Atwater was a student of von Voigt and Rubner and brought calories over uh, the from the Germans and introduced them into the USDA in 1897, talking about them as this energy force. But he was very much more considered. I would consider him, based on his research, to be more concerned about the food composition because most of his food research is about the food composition. Now, let's get into the claim. The claim is that it's thermodynamics by combustion. So let's get into some strict definitions. Combustion is the application of heat and light. So we're trying to say that this heat and energy is becoming like physiological energy. Um, And so that we could just on surface level is not really make sense. So we're going to put a pin in that and put it off to the side and see how everything else kind of lines up. Let's talk about the thermodynamics models since 1897 and that we can understand. And so we discovered the electron in 1897. Um, Planck comes up with his ideas of this universal constant. Um, Really, I could break it down into this. Like, we didn't start it until after calories are already in nutrition. And then we have this by Simon, by Sean Carroll, by this physicist. We have the pictures. Um, that is all the discoveries that have allowed us to understand molecular mechanics and atomic movement. And this is not, this was all developed after calories, 100% after calories. And so we cannot claim that calories are valid by these measures. We have to go back and analyze it. And what we've been able to analyze from these new physics measures is like things like MRI, how this works, how the muscle works. And if we go to the muscle firing, we know that the calcium moves and go over. I'm going to go over sliding muscle filament theory where myosin binds and it moves the head. And but all this waits for the calcium to bind. And then like another question is where's the energy for the calcium to move the tropomyosin? There's no ATP attached to that. It's just the calcium moving it. It's the structure. It's from the energy, atomic energy itself. And we know that the carb combustion is separated. The oxygen and the carbon never come in contact with each other. So there truly is no combustion relevance. There is no direct or indirect or delayed combustion. There is just thermodynamic energy transfer, the same way that like electricity and other things, electrochemical transfer. And so wrapping up for this last minute, um, where do we go from here? Well, all of nutrition just is based on the nutrients, the material substances that we need. And I've got it down to 11 categories of material substances. 10 of them are molecular. The 11th one is light, because these are just material substances that we need. As far as understanding the energy of the thermodynamics for like weight loss and stuff goes, that just comes from the carbon storage, so that for the pyruvate and the Krebs cycle. So if we understand how to access this storage or improve the demand for the Krebs cycle, then we would have a better pathway for weight loss than just calories in, calories out. We have a more direct physiological pathway and just don't eat as much carbon-based foods. And that's it. That's the fresh understanding of the energy. Ugh. Okay, I think I need to go over more about the electron. Ugh. I think I kind of need to do Helmholtz faster. I need to do Helmholtz, and then I just kind of like summarize everyone who was on this physiological reduction side, and then summarize people who were against it. Um, then like, but some of them were wrong for the right reasons, some of them were right for the wrong reasons. Um, and so it kind of just goes from there. Then I could get straight into von Voigt trying to give in his explanation with protein and nutrients, and then his student Rubner coming in with thermodynamics when I know it a little bit better, and then his student Atwater coming in and bringing it over, what they actually said about what they knew, because we're about to get into how we actually know stuff about the atom starting in this same year, 1897, going from there and out. And then on the development of statistical mechanics and atomic theory, and then how these benefits us. And this is actually how we discovered things like vitamins, by supposing that there were nutrients that we needed beyond these carbon sources for calories. And so, really, we just need to get into the age of material nutrition, where it is by food composition, 11 material nutrients, 10 of which are molecular, one of which is light. Uh, and any good nutritionist will be familiar with these 10 molecular nutrients: carbs, proteins, fats. Well, in order, I would like to do a different order: proteins, oils, oxygen, water, nucleotides, um, fat soluble vitamins, water soluble vitamins, macro, major minerals, micro minerals, and carbohydrates. Always last because they're not an essential nutrient, but they have major macronutrient functions. You include them. 11 macro, or the 11 nutrients of nutrition. And that's the speech. And so from here, we could talk more about the 11 nutrients of nutrition, get into the physics of those 11 nutrients. And once we're done with the physics of it, we naturally get into cooking and expand through cooking and recipes. And then it could kind of just let itself naturally reform from there. I was thinking about uh, Mike, how to handle that situation. Um, yeah, 11 macronutrients. The 11 nutrients for nutrition, cooking and culinary. And finally, we can get into exercise science. So, this next year is going to be dedicated to getting to the 11 nutrients. Yeah, this year is dedicated to getting to the 11 nutrients of nutrition. Next year, goal is to finish it past the 11 nutrients of nutrition and into physiology. That means next year for you guys, it'll be available the 11 nutrients of nutrition and then into physiology. We will be getting into physiology with the 11 nutrients and basic anatomical and physiological function from the nutritional side. From the supply side. And then we will get into signaling. And signal development. Motion and balance. Year of nutrition, year of motion and balance. Or no, the year of stability. Yeah. Stability and balance. Motion and balance. And year of dexterity, strength. A lot of work. Okay. Back to the guess that's it for the recording.